Hi all, let us heat up our life by understanding what is meant by heat. Heat is form of energy transfer from higher temperature to lower temperature. Everyone knows that heat is related to temperature. What is meant by temperature? Temperature measure the degree of hotness and coldness. And now, state the relationship between heat and temperature. Heat is proportional to the temperature. When heat increases, temperature increases too. And when heat decreases, temperature also will decrease. Once we understand the energy is transferred from higher temperature to lower temperature, let us see how the heat transfer into insulated metal bar and non-insulated metal bar. Now, let us see about insulated metal bar. Example for insulator is glass or rubber. If the metal bar is completely covered with a good insulator, no heat loss from the sides of the metal bar. By assuming no heat is lost to the surroundings, therefore, heat can only flow through the cross-sectional area from higher temperature region to lower temperature region. The red lines or arrows represent the direction of heat flow. When the metal bar is in steady state, the temperature falls at constant rate. Thus, the rate of heat flows is constant along the insulated metal bar. This causes the temperature gradient will be constant along the metal bar. Since the bar is perfectly insulated, heat is not dissipated through the wall. So the graph of temperature against distance from the hot end is a straight line with a gradient of dt over dx, so-called temperature gradient. The graph shows how the energy transfer from 100 degrees Celsius to 0 degrees Celsius. The line crossing the x-axis, so here is 0 degrees Celsius. For non-insulated metal bar, the metal is not covered with an insulator, thus heat is lost to the surroundings from the sides of the metal bar. The lines of heat flow are divergent and the temperature falls faster near the hotter and then that near the colder end. So now we can see how it is dissipated or escape through the wall. The temperature distance graph is curved instead of a straight line. It's a curve. The temperature falls faster near the hotter end, where the energy transfer from 100 degrees Celsius to 80 degrees Celsius for distance x1. So from 100 degrees Celsius to 80 degrees Celsius for distance x1. We conclusively believe that the rate of heat flow depends on change in temperature, change in distance, and cross-sectional area. Mathematically, the rate of heat flow is directly proportional to the cross-sectional area and directly proportional to the temperature gradient. You can rewrite the equation into this form. Where K is the constant known as the thermal conductivity of the material. And the negative sign shows the temperature decreasing to the increasing distance. Let me explain again what is meant by this negative sign. Let us have a look this insulated metal bar again. When the temperature is decreasing, the distance is increasing. So the negative sign shows that the temperature decreases as distance x increases. And same thing goes to non-insulated bar. When the temperature is decreases, distance increases. Define thermal conductivity. By using the rate of heat flow equation, dq over dt equals to negative Ka dt over dx. K is a ratio of rate of heat flow per unit cross-sectional area per unit temperature gradient. And the negative sign here is about the temperature decreasing to the increasing distance. So the K is thermal conductivity, dq over dt is rate of heat flow, A is cross-sectional area, and dt dx is equal to temperature gradient. For thermal conductivity, materials with large K are called conductors. Those with small k are called insulators. This is a very important point. You have to know better about what is K or thermal conductivity is about. And the unit SI for thermal conductivity is watt per meter per Kelvin or watt per meter per degree Celsius. Rate of heat flow is watt, cross-sectional area is meter square, temperature you can put it in degree Celsius, and the distance, change of distance is meter. So finally you will get watt per meter per degree Celsius. Or you can put it the temperature into Kelvin. So you will get watt per meter per Kelvin. Simple like a bubble without giving you any trouble. Table shows the values of thermal conductivity K of a few common materials. Materials with large K and with small k. For the large K are called conductors, with a small k are called insulators. Good conductors such as silver and copper have high values of thermal conductivity. Gases such as air or hydrogen have low thermal conductivity because gas molecules are far apart. Energy is transferred between gas molecules when they collide with each other. The number of density or number of molecules per unit volume for gas is low. Graph shows about two well-insulated conductors. It's about conductor V and conductor W. Compare the thermal conductivity for V and W. And is given two insulated metal bar with the same cross-sectional area. According to rate of heat flow, which is equals to negative Ka times temperature gradient, where rate of heat flow and the cross-sectional area is a constant. So, the thermal conductivity K is directly proportional to 1 over temperature gradient. And we notice that the slope for W is greater than the V. It means the temperature gradient for conductor W is greater than V because W is steeper than V. So the temperature gradient for the W is greater than the temperature gradient for the V. Therefore, the thermal conductivity for V is greater than the thermal conductivity for W. So V is a good conductor, whereas W is a poor conductor. Simple like a bubble without giving you any trouble. And how about these? We have two metals, metal A and metal B. Metal A is insulated and metal B is non-insulated. The energy is transferred from higher temperature to lower temperature, from 100 degrees Celsius to 30 degrees Celsius. And the temperature in the junction between metal A and metal B is theta. And the distance between two metals is length L. Sketch the graph of temperature against distance of the rod. For metal A, the rate of heat flows is constant along the rod. It's going to give you a straight line from 100 degrees Celsius to theta. So from 100 degrees Celsius to theta, the temperature gradient will be constant along the rod. Whereas for metal B non-insulated, the heat is lost to the surroundings from the sides of the rod because non-insulated. The metal is not covered with an insulator. This causes the temperature gradient gradually decreases along the rod and result a curved graph. Again, it is simple like a bubble without giving you any trouble. So for the metal A, when the rod is in steady state, the temperature falls at constant rate, whereas for metal B is not at constant rate. The temperature gradient for metal B decreases with distance x along the rod. Let us review the past by answering this question. Give one example of a conductor and an insulator. For the conductor, it's a copper wire, and for the insulator, it's about wood. And sketch graph on the same axis to show the variation of temperature T with distance x as heat flows through a metal conducting rod when the rod is insulated and not insulated. So for the graph temperature against distance, we can see for insulated it is a straight line, and for non-insulated it is about curve. Piece of cake, you just need a cup of coffee at this moment. Let us come to comfort zone by answering this question. A metal plate 5 cm thick has a cross-sectional area of 300 cm square. One of its face is maintained at 100 degrees Celsius by placing it in contact with steam. Another phase is maintained at 30 degrees Celsius by placing it in contact with water flow. Determine the thermal conductivity of the metal plate if the rate of heat flow through the plate is 9 kilowatt. By assuming the heat flow is steady and no energy is lost to the surroundings, the answer given is 214 watt per meter per Kelvin. According to the questions, the rate of heat flow is 9 kilowatt, which is equals to 9 times 10 to the power of 3 watt. The thickness or distance is 5 cm equals to 5 times 10 to power negative 2 meter. The initial temperature is 100 degrees Celsius. The final temperature is 30 degrees Celsius. The cross-sectional area is 300 centimeter square, which is equals to 300 times 10 to power negative 4 meter square. Determine the thermal conductivity K for metal plate. So from the rate of heat flow equation, the thermal conductivity is the ratio of rate of heat flow per unit cross-sectional area per unit temperature gradient, and we're going to substitute all the values accordingly in this formula, and you will get 214 watt per meter per degree Celsius, where the temperature in degree Celsius. Or you can put it the temperature into Kelvin, degree Celsius to Kelvin. You have to plus theta with 273 and substitute all the values accordingly again into the formula. You will get the same answer, 214 watt per meter, but now the unit for the temperature is per Kelvin. Simple like a bubble without giving you any trouble. Followed by a rod 1.3 meter long consists of a 0.8 meter length of aluminium joined end to end to a 0.5 meter length of brass. The free end of the aluminium section is maintained at 150 degrees Celsius and the free end of the brass piece is maintained at 20 degrees Celsius. No heat is lost to the sides of the rod. At steady state, find the temperature of the point where the two metals are joined. Given the thermal conductivity for aluminium is 205 watt per meter per degree Celsius and thermal conductivity for brass is 109 watt per meter per degree Celsius, and the final answer is 90.2 degrees Celsius. According to the questions, the aluminium and brass join end to end for 0.8 meter and 0.5 meter. With the initial temperature for aluminium is 150 degrees Celsius, the final temperature is theta for 0.8 meter length. Whereas for the brass, the initial temperature is theta and final temperature is 20 degrees Celsius for 0.5 meter length. Cross-sectional area for aluminium is equals to the cross-sectional area for the brass. And it is crystal clear the question stated that no heat is lost to the sides of the rod. So it is well insulated. So the rate of heat flow for the aluminium is equals to the rate of heat flow for the brass. So now we can substitute all the values accordingly into this formula, and we can find the temperature of the point where the two metals are joined, which is theta equals to 90.2 degrees Celsius. Simple like a bubble without giving you any trouble. Thank you for watching this video. Thanks a lot and thank you to the Lord.